Hello everyone, I am Savaram. I am the student from Institute of Aeronautical Engineering, an assignment report of data structures. Today our topic is graphs, convolutions and neural networks from graph filters to graph neural networks. Let's go to the topic. Introduction to graphs and neural networks. Graphs are mathematical structures used to model previous relationships between objects. Neural networks have revolutions in pattern recognitions and learning tasks across domains. Combining graphs with neural networks leads to powerful models for structured data analysis. There are so many types of graphs we can see in these pictures. Basic concept of graph theory. A graph consists of nodes, various and edges connecting pairs of nodes. Graphs can be directed or undirected depending on the nature of relationships. Graph properties include degree, adjacency, and Lipinski's matrices, which are fundamental for analysis. Requesting graphs mathematically. The adjacence matrix encodes the connections between nodes in a matrix form. The degree matrix is a digital matrix including the number of connections for each node. The graph Laplacians derived from adjacency and degree matrix is essential for spiral analysis. Signal processing on graphs. Signals on graph analysis data varies to each node, enabling analysis of structured data. Graph uh, graph transform allows for frequency domain analysis. Analysis of science. Spiral models utilizes eigenvalues and eigenvariates of level of flittings. Introduction to graph filters. Graph filters modify signs on a graph to or surprise certain features. They can be designed in the spiral domain based on the eigenvalues of the Lipinski's. Graph filters are crucial for tasks like denoising, smoothing, and feature extension. Concluding of graph. Convolution on graphs generalizes classical conclusions to irregular demons. It is a defined either the special demon or via locational spectral operations. Spectral conversions involves multiplying the graph Fourier transforms of signals by filter functions. Spectral graphs convolutions. Spectral convolutions employs agent decompositions of the Laplacian to define Filtering. Filters are represented as spectral multipliers applied to the graph Fourier basis. This apologize can be computationally expensive for large graphs. Spectral graph spectral graph convolutions. Spectral methods define convolution directly through local neighborhood adjacencies. They are more scalable and influence aggregation features from neighborhood nodes. Examples include graphs like GAT and other message passing frameworks. From graph filters to natural networks. Graph filters serve as the building blocks for natural network achievements of graphs. Neural networks learn optimal filters through training to capture complex patterns. Combining filters with learnable parameters leads to powerful graph-based models. Graph Natural Networks (GNNs) GNNs extend neural networks to operate on graph structured data. They leverage local neighborhood information to learn node, edge, or graph level representations. GNNs have achieved state-of-the-art results in the various domains like chemistry, social networks, and communicated systems. Architectures of GNNs. Architectures of GNNs. GNNs layers consists of message passing, ag- aggregation, on update steps. During message passing, nodes exchange information with neighbors. Aggregations futures combine neighbor information to update node futures. Training and optimizing of GNNs. GNNs are trained using grad gradients based gradient based optimizing method. Methods are similar to standard neural networks. Loss loss functions depend on the task such as classifications, regulations, or link predictions. Predication. Regulations technologies helps prevent overfilling on graph data. Applications of graph natural networks. GNSS or GNNS are used in drug mm, discovery of printing modulators properties. They utilize social networks analysis and communi- communicate detections. GNNS also improve communicated systems or traffic forecasting. Challenges in graph neural networks. Scalability is scalable to large graphs remains a significant challenge. Handling dynamic or including graphs requires advanced models, ensuring interindividual and understanding leader relationships in the ongoing research area. Future directions in deep learning, developing more developing more scalability and effective GNN is a key force in integrating multimodal data and heterogeneous graph presents new operations. They are going ongoing research to technology theoretical understanding and exploiting of GNNs. Similar summary and key takeaways. Graph provides a natural framework for modeling relational data. Convolution on graphs extend classical sign processing to irregular domains. Processing to irregular domains, graph neural networks combine this concept enable learning on mm, structured data. Conclusion: the evolution from graph filters to GNNs marks significant progress in the structured data analysis. Advances in the field continues to impact many areas of science and technology. Ongoing research promises even more powerful and various graph-based and learning methods.